So today, for the most part, is not really pulling anything new into it. It's just taking everything we've done in this chapter and pulling it all together. Now, we know that we can go ahead and find all this information, that you find your max and mins increasing and decreasing from your first derivative and doing your labeled number line. You get inflection points and concave up and concave down, you get from your second derivative for a labeled number line. X and Y intercepts is from your original function when you either plug in 0 for X or set it equal to 0. Remember vertical asymptotes and discontinuities, that's from when like the bottom is equal to 0. End behavior is what happens when you go far to the right and far to the left. Does it level off at a horizontal line, which would be a horizontal asymptote, or does it have a slant asymptote or an oblique asymptote? Using all that information, you can then get a fairly accurate graph of what's going on. So if you did an accurate graph of this with all that information up there, you would get what we have over here on the right. So let's go ahead and find all that information for this particular problem here. Now, your y-intercept is when you go ahead and plug in 0 for x. Well, if I plug in 0 for x, I get negative 1 over negative 1, so I get a y-intercept being 1. Zeros, all you'd have to do is set your function equal to 0. And the only way a fraction is equal to 0 is when the top is equal to 0. So if you set the top equal to 0, it's a nice normal quadratic. It doesn't factor. You use your quadratic formula. You get these to be zeros. However, for the sake of graphing, it's going to be a lot easier to have decimal approximations. When you're looking at your derivative and things like that, you may find it easier to go ahead and write this in a different form. You could do longhand division if you divided the top by the bottom, or in this case, because you're dividing by x plus number or x minus number, you could do synthetic. But if you do your division, you would go ahead and get this with a remainder of 1 over what you were dividing by. Some people will find this easier to deal with for taking the derivative. Other people will find this easier to deal with for taking the derivative. It doesn't make a difference which one. So in taking your derivative, I'm going to do the derivative of the x, which I know is 1, derivative of 2, which I know is 0, and then all I have to do is just do the derivative of this. And well, when I do the derivative of that, I would get this here. Because this is really just an x minus 1 to the negative first power. Then you just have to do the power rule, or you could do the quotient rule. Either way, you get this. Now, you could either leave your derivative like this, or you could write it as a big fraction. If you did that, you have a common denominator here. So you'd have to go here, whoops. On the first fraction here, you'd have to go x minus 1 all squared over x minus 1. You get this here. Now, foiling out the top, then doing your minus 1. The 1's drop, you would get this. So your critical points are when the top is equal to 0, which does factor, which would be at 0 and at 2, or when the bottom is 0 for your critical points. Because remember, your critical points are where your derivative is 0 or undefined. So if you do your derivative being equal to 0, that's from the top. Derivative is, derivative undefined is from when the bottom is equal to 0, and that's our 1. Remember, label your number line. This is from your first derivative. Make sure you have it labeled as your first derivative. Try a number to the left of 0, like negative 1. Plug a negative 1 here, negative 1 here. You get a negative times a negative on top, which is positive, over something squared on the bottom, which you know is positive. So you get a positive, so you know your original function would be increasing. Try a number in between, like a half, 1/2. My 1/2 then minus 2 would be a positive times a negative over something squared on the bottom. So it would be a negative over positive, which is negative, so you know you're going down. And then you could try something like 1/2. 1.5 here, 1.5 minus 2 is negative, so you get a positive times a negative over a positive on the bottom is also negative, so you know you're going down. And then you try something to the right of 2, and then everything ends up being positive again, so you know you're going up. Here at 0, we're at top of the mountain, so we know we have a max. Here at 2, you know you're bottom of valley, so you'd have a min. So to find that max, you just have to go ahead and take 0 and plug it into your original function up here, and that's where the 1 comes from. Your min, x coordinate is 2. To actually find the y value, take 2, plug it into either one of your original functions, and you would get 5. So what's going on here at 1? Well, it could be an inflection point sometimes, but remember, your original graph was undefined at 1, so that's a vertical asymptote. So it's not a point of inflection, it's a vertical asymptote. So now, at this point, I'm going to probably go ahead and use this to find my second derivative, because it's easy to know that the derivative of that 1 in front is 0. And this is just a negative 1 x to the negative 2, so we can just do the power rule. Well, when we do our power rule there, we get this. Critical points then, when is the top equal to 0? Well, the top's never 0, it's always 2. Well, what will cause the bottom to be 0? Well, 1. So we only have one critical point, and that's 1. So we can put that on a labeled number line. Try a number to the left of 1, like 0. 0 minus 1 is negative 1, cubed is negative. Top's positive, bottom's negative, so we get a negative, so that means over here to the left of 1, we're concave down. Try a number to the right of 1, like 2. 2 minus 1 is positive. Positive cubed is positive. Positive over a positive is a positive. So you know to the right of 1, you are concave up. So you're concave down to the left of 1 and concave up to the right of 2. And we're switching concavity here. But remember, x being 1 was our vertical asymptote on our original graph. So it's not a point of inflection. Yes, we're switching concavity, but 1 is not part of your original graph, so it cannot be a point of inflection because that point has to be part of your original graph. So remember, you have that. Your end behavior is your limit as you approach infinity. So you look at your limit as x approaches infinity. It's easiest to do that of this right here. As x gets really, really big, this last fraction here goes to 0. So it really just leaves you with this x plus 2. So that would be your slant asymptote. Basically, your slant asymptote is after you do your division, after you do your division here, your slant asymptote is the quotient, not the remainder. Your quotient is just this first part. Remember, the second part was from your remainder. But that's why, because that remainder part is over a number over x, and when you plug in something big, it goes to 0. Plotting all that, we would get this. So here, do the same thing. Your x-intercept is when you plug in 0 for y, so you set this equal to 0, when you solve it, you get this. Your y-intercepts when you plug in 0 for x, plug in 0 for x, and you get this. Your first derivative, well, you'd have to do quotient rule. You would get this here. So you set the top equal to 0. Oh, the top's never 0. Well, you set the bottom equal to 0. The only way the bottom's equal to 0 is when this is equal to 0. If you square something and add 2, it's never 0. So you have no critical points in the top and no critical points in the bottom. So it's always either increasing or always decreasing. But the top is positive, the bottom's positive, so you know it's always increasing. So your graph is always going up as you go to the right. By the way, for your end behavior, that's what happens when you're plugging in big numbers here and big numbers here. This plus 2 doesn't really do a whole lot. So for the most part, when you're looking at end behavior, it's like x over the square root of x squared. which is really x over like the absolute value of x, if I can write so you can read. Because we know that squared undoes the bottom, but we know it has to be positive because that's in front of our root. So we know the end behavior is like this. So if you plug in a big positive, the top would be positive, the bottom would be positive, it'd be the same thing top and bottom. So we end up getting 1. So we have a horizontal asymptote of y equals 1 when we go to the right. When we plug in a big negative, the top would be negative, but the absolute value would cause the bottom to be positive. One's positive, one's negative, so that means we end up getting -1. So that's your end behavior. When you go far to the left, you level out at a height of -1. When you go far to the right, you level out at a height of +1. We got to also look at our second derivative. So you do the derivative of this, which you could just do 2 times x squared plus 2 to the -3/2 and do the power rule. Well, we just get this. Well, you got to look for critical points. So you got to set the top equal to 0, which is 0. Set the bottom equal to 0. The bottom's never equal to 0, so you only get one critical point, and that's when x is 0. So you put that on a labeled number line. Try number on each side. Try number to the left of 0, like -1, makes the top positive. The bottom's always positive. Positive over positive is a positive. Try number to the right, like 1. 1 times -6 is negative. The bottom's always positive. Negative over positive is negative, so it means we're concave down. So we switch concavity. It's probably a point of inflection. Double check your original function, though. Does 0 work in your original graph? Yeah, well, you don't have any issues with dividing by 0 when you plug in 0. So it does work. So 0, 0 ends up being a point of inflection, because 0 is part of the domain of the original problem. If it was where you had a vertical asymptote from the original problem, then it would not be a point of inflection. So graphing everything we just found from the above problems, you would end up getting a graph that looked like this. So here, if we look at this graph, it's a periodic function, so it's going to repeat every 2 pi, because remember, to find your period, you can use the peanut butter equation from pre-calc, that your period times your b value, which in both cases is 1, is equal to 2 pi. So for the sake of this problem, we're going to only look at one period from -pi/2 to +3 pi/2. You should also realize you have some domain issues at what causes the bottom to be 0. Set the bottom equal to 0, and that would be when is sine equal to -1, and sine's equal to -1 at 3 pi/2, or any full revolution thereafter, and that's what we're saying down here in blue. So, to find your first derivative, well, we could also find your x-intercept. That's where you cross the x-axis. That's when it's equal to 0. The only way a fraction is equal to 0 is when the top is 0. You think of when is cosine equal to 0 on that interval, and it's only at pi/2. Your y-intercept would be when you plug in 0 for x, plug in 0 here, plug in 0 here, and you get 0, 1. Your period is 2 pi. We already talked about that. Your first derivative, you could use your quotient rule, derivative of the top times the bottom minus the bottom times the derivative of the top over the bottom squared, and it simplifies down to this. Now, notice, sine's always between 1 and -1. Plus 1 would make it between 0 and 2. A -1 on top over something between 0 and 2 is always negative. We don't have to be concerned about the bottom being equal to 0, because it's only 0 at the endpoints of our domain that we're graphing. So it's always negative, so we have no critical points. So, oh, I think this is wrong. It's always negative, so therefore it's always decreasing, not increasing. Then we also have our second derivative. Well, you can do your quotient rule again, And well, you get this. So you get critical points from the top being 0. Well, when is cosine equal to 0? Well, cosine's equal to 0 at the top of the unit circle, pi over 2, and bottom of the unit circle, 3 pi over 2. Now, pi over 2 is part of our domain. 3 pi over 2 is at the end point of our domain. So our critical points are basically going to be pi over 2 from it being equal to 0, and then where is it undefined? That's really the endpoints of our domain. So all we'd have to do is put those on a number line. It's actually not a number line. This is a numbered line segment because we have endpoints, with our endpoints being the end of our domain of negative pi over 2 and positive 3 pi over 2. Our only critical point right here, pi over 2, we throw in here. And then notice it's a labeled number line. We try a number in between here and here, like 0, cosine of 0. The bottom is squared, so we know it's positive. Cosine of 0 we know is positive. A positive over positive is positive, so we know we're concave up. Over here we could try something like pi. Cosine of pi is -1. Plug in pi down here. We get, because of the squared is positive, negative over positive is negative, so we know we're concave down. And this would be a point of inflection because we're switching from concave up to concave down. Once again, to find the y value of that point, plug it into your original function. Also, we'd have a vertical asymptote here and a vertical asymptote here because that's where your original function is undefined. That's what causes the bottom to be 0. So vertical asymptotes, we just talked about that. Horizontal asymptotes. Well, would it level out at a horizontal line? Nope. Critical points, not really. Possible points of inflection, yep, we found that right here at our pi over 2. So when you graph all that information, you get this shape right here.